What's up, guys? So welcome to part 2 of our attempt at LeetCode question 145, which is binary tree post-order traversal. So if you remember from our last video, we attempted a solution that was maybe more or less not quite ideal. It wasn't like the cleanest solution. It definitely worked, and it was of I would say, acceptable time complexity and space complexity, but it wasn't the cleanest or most elegant code. So for this question, let's go over an similar iterative approach, but it's going to be a lot cleaner. So let's get started. So for those of you who don't remember from the last video, or if you haven't watched it yet, and I'll post a link in the description box below to the previous video, but let's quickly go over what exactly is post-order traversal. So post-order traversal has a fairly straightforward definition, which is given a root, you visit all the nodes in a left subtree first, and then you visit all the nodes in a right subtree, and then finally you visit the root node. And I guess I should say by visit, it's not really visit. You are visiting it, like you are looking at it, so to speak. But in terms of outputting what that node is to the final like result list, that's kind of what I mean by that. So just a quick example here. So for the one that they give us, which is, you can see there's a root of 1, which has a right subtree of 2, and then 2 has a left node of 3. So in this case, let's start at 1. So we're always starting from the root node, the given node. So remember, we're looking at the left subtree first, right? So for 1, there is no left subtree. Okay, so that's fine. But next, we look at the right subtree. So we notice that 1 does have a right subtree, which is this node that starts with 2, this node of 2. Okay, that's great. So now we visit 2. And then we repeat the same thing again, which is we start looking at the left subtree of 2, which is 3, right? So great, it has a left subtree of 3. So now we visit 3. Do the same thing again. Does it have a left subtree here? It does not. So we go to the next step, if you will, which is look at the right subtree. So 3 does not have a right subtree, so we're good to go there. So now we go to the final step, which is the root, which is just 3 itself. So at this point, we output 3 to the output array, which you can see they already listed for us here. Let me zoom in a little bit. Okay, let me pull this side. There we go. Okay. Great. So now we outputted 3. So now we've handled 3, so we bubble back up to 2. And remember, we already visited the left. This is where it gets a little confusing, and maybe it's a little recursive. It can be a little confusing remembering, like, you're going down the tree, like which step are you at? But this is a fairly simple example. But so remember, we already visited a left subtree of 2. And we end up outputting 3. So now what's the next step? Next step is we visit the right subtree of 2, which doesn't exist. So that's fine. So finally, we visit the root of 2, which is just 2 itself, and we output that. So that's what we're doing here, is 2. And then you can kind of see like the pattern continues on with 1. Remember, we already checked the left subtree of 1. We are now we're just finished checking the right subtree of 1. So we handled that by adding 3 and 2. So now we're bubbling back up finally to the topmost node, if you will, and we just output 1 in that case. So that's kind of what post-order traversal is. So now let's go to the drawing board and see if we can think of a cleaner solution than we implemented last time. So let's start off with a simple example that I've already kind of drawn out here. So this question is interesting because it's easier to think recursively because you're doing the same thing over and over again with each node, which is like we just mentioned about what is post-order traversal even. It's for each node we're outputting all the nodes on the left side first, and then the right side, and then the root itself. So that kind of lends itself to like easier, I suppose, recursive thinking. But for our case, we want to try the harder solution, which is iterative. And in my last video, I made an attempt to essentially traverse down the left side of a given node first. So if you remember, we had that while loop that essentially just went all the way down. If you can imagine this was longer, maybe 3 was here. Draw this out. Get rid of this. Yeah, if you can imagine, the first thing we did in that solution was to travel down. So go from 1 to 2 to 3, and then perform some operations on it. That ended up being a fairly messy solution, not the cleanest. So let's think of another idea. And for this idea, let's try to use stacks in a better way. So let me move this back up here. Let me Control Z. Okay. So you might ask, if you're starting at this question from scratch, and part of it is just experience working through these binary tree questions and working with stacks and queues and all those data structures. But one thing you might wonder is, okay, if I haven't really worked with it as much, how do I get that intuition to use a stack? Well, in this case, a stack, if you look at a definition of stack, the stack lets you access the most recently added elements of a list, right? So in this case, if you remember, if we go back to our example here, we were traveling down the nodes and kind of going back up, if you remember. So remember, we were checking 1, and then one does not have a left, but then we looked at the right subtree of 1 and then kind of went to 2, and then so on and so forth until we bubbled up. We added 3 to the results and bubbled up and added 2, so on and so forth. So you can kind of see there's a certain order that you're visiting these nodes and performing operations on them on. So in this case, it would make sense to use a stack because you only care about what the most recently, or not only care about, I should say, but you want to be able to access the nodes in a manner of the most recently added nodes, right? Because that's what you want to perform operations on as you go back up the tree, so to speak. So let's think for this example. Let's start off with, let me get my text here. Actually, this might be a little better if we just go ahead and split this into 2, just because we can have it side to side, like in our previous video. Let me move this over here really quick, just so we can have a code editor to kind of work with here. There we go, a little bit better. Okay, so what if we start off with this? Let's say we're doing some kind of operations on, we're kind of moving through this tree, right? And as you're moving through this tree, one thing you'll often see is you'll pop off a value or pop off an element from the stack and do something with it. So let's say in this case, let's just start off with stack.pop, right? So say we're given, I don't know, this is gonna be very pseudocode for the moment. Say stack.pop, we're given a pop value, a pop node, I should say. Let's make it really explicit. A pop node. And, oops, make it a little bigger. Okay. So say that's the node that we're currently looking at, right? That's a node that we currently want to apply this post-order traversal logic on, right? So one thing you can say is, okay, we pop off this node from the stack. Now we're looking at it. What do we care about? Well, one thing we care about is whether or not this node has been visited before. Because if you remember back to our example here, when we were traversing down, I shouldn't say just down, but we're basically traversing up and down a tree, if you want to think about it visually, because we were going down and then remember going back up and adding adding nodes to the results list. So in this case, you can think, all right, remember when we went down 1, 2, and 3, this path? So we checked 1, we checked 2, and then checked the left subchild of 2, which is 3. and then we kind of bubble back up, things back up. So you can imagine, like, we're basically touching, in this short example, each node twice, right? So we need to know if we've actually seen this node before. Like, we actually perform our operations on this node, because if we have, then we don't want to do those operations again. So in this case, one thing you can say is, okay, let's just use some pseudocode. If pop node has not been visited, right? That means this is the first time we're looking at it, right? If it has not been visited, then what do we want to do with it? Well, let's think about this. Let me move back here. So if the node has not been visited, then in this case, it means that it could potentially be an element that we add to our results. So in what case do we add an element to our results? Well, to add an element to our results, the following have to be true. The node has to not have any children, right? If pop node does not have any children, which is basically a leaf node, or, so just kind of like going to this example, hopefully this isn't that much more different from the example that we went over in the beginning, but as you can imagine, say we're down at 2, right? So we traverse down to 2, and now we check the leaf node. We see that 2 doesn't have any children, so that should be an automatic sign to add that to the results list, right? So that's the first case, if the pop node does not have any children. Or the node, and this goes back to our example here. I'll just switch it back here just for make it simple. So now we're looking at example 1 here on the left side. Remember, once we traverse all the way down to the end of the tree, we've added 3 to results list, and we've gone back up to 2, right? So now we're checking 2, but 2 does have a left child, but remember, we already visited 3, right? We already handled 3. So in this case, we don't want to visit 3 again, because that will cause an infinite loop. So we need some logic here, which is that, or the pop node, in this example we just went over, 2, pull it over, or pop node does not have any visited children, right? Which is saying both children have been visited. So if this is the case, oh, sorry. Let me go back here. Or pop node has visited children only, right? Because it might have just one child, and that child will be visited. So the pop node does not have any children, or if it does have children, all of those child nodes have been visited already, right? So if that's the case, then we want to append that to the results. So append, or we say, let's just use the more formal term, I guess. Though either one works depending on the data structure that you're using and the language. But we push pop node and technically the value onto results, right? So and again, this is all pseudocode. Okay, great. So, but what if the node has not been visited, right? Let's say we go down this part of the conditional. So the node hasn't been visited, but it does have So basically here, if the pop node has non-visited children, right? If the pop node has non-visited children, then what we want to do is oh, I'm sorry. Actually, we don't technically need this part because if we reach this part of the code, that means it didn't let's see here. How should I say this? If pop node has not been visited, if pop node does not have any children, or pop node has visited children only, then okay, if pop node has non-visited children, then we can say we want to push. I'm gonna get really generic code, really pseudo code-ish here. Push children onto the stack, right? Because that means we want to visit those children. And the way we visit those children is you can imagine this is inside of like a loop, right? Because we're continually doing things, traveling over an entire tree. So there's some kind of loop, and we push children on a stack, and then we go back to the top of the loop, and then we pop off the node, and that's the node that we're looking at, right? So going back to here, like what does it mean to push children onto the stack? Well, in this case, we want to prioritize moving or visiting the left subtree, right? So in this case, we can push node dot. Now you might want to, the intuition might be to push the left child first, something like this, push node dot left onto stack, and then push node dot right onto stack. But if you think about this, what are you doing? You're pushing the left child on, and then the right child. So the most recently added element was the right child. So when you go back up to the node, the top of the loop, when you pop off the stack to obtain the node that you're currently looking at, you're essentially getting the right node because it's most recently added. But that's exactly the opposite of what we're trying to do with visiting left subtree first, and then right subtree, and then a root. So it's actually reversed. So it's a little counterintuitive, but this needs to be reversed. Okay, so this is what that means basically. And also, we would need to, let me think, push we also need to push the node onto the stack as well, right? And this is a little more part of like the trickiness of this question is that it's like, okay, we popped off the node, right? So it's like we're looking at it. We popped it off the stack. We're looking at it. But why are you pushing it back on? Well, that's because number one, it makes the code cleaner. Like if we didn't have this logic, this would be a lot messier. So this is kind of to counterbalance this part here by pushing the node back onto the stack, right? And I should be more specific. Push pop node onto stack here, right? Because you're taking off the stack and you say, okay, I'm looking at it. We don't know for sure if we want to add this node to the results list, and that's where we apply these checks. If the pop node does not have any children or pop node has visited children only, that means we've already seen its children, right? We've already performed operations on them. So we definitely, in this case, push the pop node value into the results. Else, if the pop node has non-visited children, that means we want to keep on going down the tree. So that means we haven't worked with pop node. We haven't pushed the pop node's result value onto the results. So we want to push it back on. It's very counterintuitive, right? This is part of why LeetCode is so tricky. Is that all these things are, always like little tricks here and there. But hopefully that kind of makes sense intuitively somewhat, right? Okay, so Yeah, I think that is. Let me think. Let me go back to this conditional here because we didn't handle the case of what if the pop node has been visited, right? So if it has been visited, well, I guess if it has been visited, and this is why this is kind of nice. If it has been visited, then we don't do anything with it. That means we've already handled it. That means we've already added that to the results list. So we don't want to apply any of these operations. So we don't need like an else here. Else, has been visited, do something. We don't want to do anything. So in this case, cleanly enough, we can just get rid of this else statement, right? And just have this loop here, right? Okay. So in this case, maybe we can start. There might be some edge cases that we haven't really gotten to yet, but or maybe there might be a bug even in this code. I remember all these videos I'm doing them kind of more or less live because just to kind of give you guys a real time sense, like an honest sense of how I think about these things. Again, I apologize if my LeetCode experience hasn't been quite refreshed yet because I haven't done LeetCode in a while, but hopefully you can kind of like join this journey with me and kind of work with me through this live more or less. So okay, let's do this. So let's say loop pop node. Let me actually open up, and this is a good habit to get into. Sometimes like it's hard, I know, because like it can be quite time consuming to do dry runs, but in this case it might be worth it. So let's go here, zoom out a little bit. All right, so let's try to do a dry run and see how this runs and then find any bugs, because oftentimes, especially working professionally in large code bases, you will find bugs. Like it's very rare that you don't find bugs in your initial implementation. And that's totally fine. The key is to iterate, to find those bugs fast and to fix them fast, and repeat that process if necessary. Of course, there's certain times you want to slow down and try to get the right implementation out first before iterating, but it depends on how critical your product is or your feature is. There's some features that are more important to be right the first time. There are others that not so important, and the trade-off or the gain that you get from being iterate faster is you save a lot of time because you can kind of get immediate feedback, user feedback, when you release it to production. But I digress. We can talk about that in another video, kind of like professional tips and all that. But all right, so let's get started with this dry run. So basically, I'm just gonna follow this here. Let's move it up a little bit. Okay, so all right, let's just comment in here. So we have some kind of loop. So the loop is probably going to be, and this is pretty common. You'll see when you're doing questions that involve a stack, or when you're visiting nodes, in some kind of order, is that the outermost loop is to check while the length of the stack is greater than 0, which means that essentially means that while you still have nodes to visit, right? Because if you run out of nodes to visit, that means you've handled all of them. That means you've done operations on all of them. That means you can stop. That means you finish. So while length of stack is greater than 0, right? So let's start stack.pop. Okay, but this requires essentially, again, I'm doing a little bit of dry run, also refining my code at the same time. Okay, so let's say root is 1 for our example on the right side again. Let me move this down. Let me make it really big so you guys can see it closely. There you go. So stack includes 1 at first, while length stack is greater than 0, which is the case. Stack.pop. So now pop node is 1, right? If pop node has not been visited, and again we'll discuss in a minute when we actually implement how we can denote that something has been visited. So if pop node has not been visited, which it hasn't been, then we go to another check, which if pop node does not have any children, or pop node has visited children only. So neither cases are true because we're just starting out. So we bypass this check here in line 16, go to line 19. If pop node has non-visited children, Awesome, which it does. So in this case, we push pop node into stack, so we're kind of pushing it back onto the stack. Remember, we popped it back off. We popped it off earlier. Push the right child, which is 1, 3, and then the left child, which is 1, 3, 2, right? Okay, let me zoom out maybe a little bit. Hopefully this is still large enough for you guys to see. Actually, I really want to make this like, yeah, there we go. It's a little better. Move this to the side. Okay. All right. Cool. So now we enter the top of the loop again. So now we stack.pop, which is 2 in this case. So now we're looking at a left child, right? So now we're working with the left child. If pop node has not been visited, which it hasn't, and we check if the pop node does not have any children, which it doesn't, right? So this is where it gets a little interesting, because now we push the result of 2 of that node into the results list, right? Okay, that's awesome. If pop node has non-visited children, okay, so this is where like the code, and you can see a little earlier this if conditional gets a little strange because it's not an else if, but essentially, let me check here. If pop node has non-visited children, which it technically does because its children are none, right? Children are like don't exist, so technically haven't been, but we haven't visited them yet either. So, let me see what happens here if pop node has non-visited children. This might be a source of a bug. Pop node has non-visited children. Push pop node onto stack, which is pushing 2 onto the stack. Oh, I should say another thing is, okay, I see there's a bug because I want to say maybe we can just continue with this because even though its children are none, if we continue with this, lines 20 to 22, it'll push none into the stack. But maybe that's okay because we can handle that in the code. Like it'll pop off a none node it'll pop off a none node and we'll be handling a none node, but we can check that in the code probably. So yeah, so what we can do, I see 2 things. So one thing is a none nodes, which is on line 21 and 22, right? Because again, pop node is 2, which doesn't have any children. Another thing is we're pushing 2 back onto the stack, but 2 has already been like, we've already handled 2 because we already pushed it into the results. So one thing we can do is, this is another thing. Is we need to, because we need to set the node as has been visited already. Has been visited. So we need to set pop node or add pop node to visited, whatever data structure we eventually use for visited. So add pop node to visited, and so this will handle the. As you can see, this is gonna handle the case where if we push the pop node back onto the stack, and remember the pop node we've already added results list, line 15 is going to handle the fact that it's already been visited, right? Because we only do all this logic if pop node has not been visited. So it's okay to push it back on the stack because we already set it as visited up here. A little tricky, I know, but I think this will work. So we kind of like reasonably, the reasoning came through this. It wasn't just like some kind of magic trick, right? So that will handle this line 21. What about lines 22 and 23 where we add the none to the stack, right? Well, quite simply, we can check if the pop node even exists. So we can say if pop node is not none, or you can say exists is not none. Just do it's not none, and kind of just like kind of nest all this in here, right? Because then this will handle a case where, you know, we're pushing none nodes into the stack. Okay, so basically, I'm not gonna go through that again because I'm not gonna go through the rest of this. What happens down here when we enter this part of the code. So I know a lot has been said since we've kind of like done the example, but basically we're at this step here, if line 21, and remember we push results onto the results list, and we've also, let's say visited contains, it's like some kind of set, right? Contains 2, right? So we've already done this, and then we're gonna go back here, and basically what's gonna happen is we're gonna push pop node back onto the stack. And I should say, actually stack is gonna be 1 and 3 in this case. So we're pushing, so it's gonna be 1, 3, and 2, right? Let me get rid of this. So it's not gonna be, this is from the previous run, the previous iteration of the loop. But yeah, as you can see, like, we're going to, and then stack is going to be 1, 3, 2, whoops, 1, 3, 2, none, and same with the left, but let's not go over that. But basically, these if conditionals are going to handle, these if conditionals of checking that the pop is not none and the pop has not been visited are going to handle this, like, the stack here, right? So we can kind of like skip the rest of this logic down here, and we can kind of go on from it. So let me go ahead and get rid of this. Let's see. So we added 2, and then we've done all this stuff with the left and right child. That's great. So stack is going to be 1 and 3 still. Let's go back up to here. So basically, all right, eventually after all these checks happen, with all this stuff of the none nodes, we're going to be still left with 1 and 3 in the stacks, right? So let's start up back up here. Sorry if it's a little confusing. So stacks is going to be 1 and 3. And then we pop off 3. So actually it's going to be, sorry, what I mean by 1 and 3, it's going to be a 1 and 3. Ooh, it's raining super hard outside. It's going to be 1 and 3 up here at the very top of the loop. And then we're going to pop 3 off, and stack is going to be 1, right? So now we're dealing with 1. And pop node is not none, which is not. If pop node has not been visited, which it hasn't been. Like we've maybe I probably should have mentioned this earlier, but visited essentially means like we've done an operation on it, we're done with it, right? Because we've visited one before. If you define visit as like you set to a variable, you've seen it, like you're visually, if you think of it from like a diagram or a graphic sort of way, you've kind of like gone through it, right? But we haven't added 1 to the results list yet, so it has not been visited. If pop node 1 does not have any children, or pop node has visited children only, so neither of these are the case, so we skip this line 18 check, go to 22. If pop node has non-visited children, which is the case, we push pop node onto the stack. So this is where it gets interesting again, right? So we push 3 back on, so it's already been visited. This is actually correct. 1 and 3. Stack is 1, 3. Push back 1 and 3. Push. Interesting. So we're pushing. Oh, sorry. I'm jumping the gun. Sorry, guys. So I'm actually looking at this part. Let's get rid of all this. We can leave the comment there, but we're looking at 3. Sorry, I was looking at 1. We're looking at 3. So again, 3 has not been visited. It's not none. It exists. If pop node does not have any children, so it satisfies this case. So great. So now we're going to push 3 onto results. So the results, remember earlier was 2. It already contained 2. We're going to push 3 into the results. Add pop node to visited. And remember, it already contained 2, so we're just adding 3 to the visited set. Um, now we go here. If pop node has non-visited children, and just like the case for 2, it does, even though the children are technically none. So now we're going to go through the same flow that we already went over with 2, so we can skip that. But essentially what's going to end up happening is that we're going to bubble back up to 1, right? So let's bubble back to 1. So stack is, let's go back up here. Let's update all these variables here. Stack is going to be 1. Let's pop it off. So pop is going to be 1. Stack is now going to be empty, right? And if pop node is not none, which is the case, pop node has not been visited, which is the case. If pop node does not have any children, or pop node has visited children only, and remember, we visited 2 and 3, as you can see from this previous setting of the visited list or visited set. So we're going to enter this part of the code, push 1 into results, add 1 to the list. And then continue on. If pop node has non-visited children, which it doesn't, we visit everything. We then just go finally back up to the top of the loop. And remember, now stack is empty, so we break out of this and return results. So, okay, so from this kind of dry run here, I know it's maybe a little bit hard to follow. You know, these dry runs are always a little tricky, so definitely rewind the video, go slow over it if you need to. Or better yet, you know, try it on your own and kind of use the video as some guidance. This dry run, according to that dry run, this code should probably work. So let's get to implementing this code. All right, guys, so I basically just went ahead and coded up the implementation based off of exactly what we were just looking at in terms of the pseudocode. So yeah, just kind of took what we had here. This is already I commented out, but just keeping it here for reference. I basically translated this to the code implementation up here. As you can see, there are some helper methods, because if you look in our pseudocode, there's some logic with if the pop node does not have any children or the pop node has visited children. So I created some helper nodes, because otherwise it might get a little cluttered in the actual meat of the solution, which is on lines 23 to the end of this class here. So I'm going to try and run this. Run this here. All right, so for the simple solution, or a simple example, it works. Let's go ahead and just try it for the, as you can see, I actually tried running this earlier, so, and I already know that's gonna work. So yeah, so it looks like it passed all the test cases here. Awesome. So yeah, so this is definitely, I would say, in my opinion, from our last video, an improvement. It uses the stack property a bit more cleanly than our last implementation. I will say, however, if you look in the discussion part of LeetCode, there are some, you know, there's like a ton of solutions here. There are even cleaner ones than this. Like this one, I'll say it's cleaner, but it's still like not quite, you know, if you did an interview, maybe it wouldn't really honestly blow the interviewer's mind away, just because, you know, there's still quite a few lines of code here, as you can see with these helper methods and stuff. So there's a pretty clever implementation in the discussion section, which I'll point to right now. So if you go discussion, you kind of sort it by the most voted solutions. There's this one created by this Da Shen guy, or a female, and share my 2 Python iterative solutions here. So I would click on this if I think this is a pretty clean implementation, if you will, especially this one. This is super clean. I mean, no helper methods, anything, and the way they use the visited as a tuple instead of what I'm using with taking the ID of the object and storing that ID in the visited map. It's a lot cleaner, I would say. So, you know, go take a look at this. You know, it's a pretty clever solution. He also has a second solution. But yeah, so this is my implementation. I'll just kind of let me kind of zoom out a little bit. So if you want to pause and kind of take a look at it, let me scroll down a little bit. There we go. Let me move my face out of the way, all the way up here. So starting from the top. Yeah, and again, this is just the implementation version of what we went over in the dry run with all the pseudocode. And yeah, so this is you know, a bit of improvement, like I said, over our last solution. Still not quite honestly where I want it to be. I wish I came up with that solution that I just showed you in the discussion section. That was super clean. But again, this is a bit of a tricky question, I would say. It's definitely not in, again, it's my opinion. I don't think it's really quite an easy, maybe between easy and medium, even though I've seen mediums that I can just do just like that, just super easy. But it's not the most intuitive implementation to do iteratively. So, this is a great exercise for learning stacks at a deeper level, I believe. So definitely, if you have time, go through this and really try to understand the intuition behind it. Because in the future, if you use stack questions, it'll really help you kind of understand it at a deep level and be able to use them at a deep level and quickly when you're actually doing the interview question. So yeah, so leave any comments, feedback below. Any questions, please leave below. And this is the first time I'm starting to say this, but hit subscribe if you're interested. I'm going to keep on posting these kind of videos. Hopefully you guys can join me on this journey of just general growth, but also specifically growing through LeetCode and just making videos. And I'm with each video, trying to make them better and better each time, just so you can kind of understand like intuitively how these solutions come about and not just kind of throwing a solution at you. Because those solutions, anyone can copy those solutions from the discussion section, but the reasoning is the most important thing. So, guys, if you have time on your own, definitely read through this question and try to implement it yourself and try to really grab that intuition on your own if you can, and use this video as help. So awesome. Thanks, guys. See you next time.